Okay, so let's start with the next tutorial on supervised learning, which is again dealing with the time series analysis. Now, a time series is a series of data points ordered in time that we have already seen in the previous tutorial, and time series adds an explicit order dependence between observations, a time dimension in a normal machine learning dataset. The dataset is a collection of observations that are treated equally when future is being predicted. Time series regression is a statistical method for predicting a future response based on the response history, known as autoregressive dynamics, and the transfer of dynamics from the relevant predictors. Time series regression is commonly used for modeling and forecasting of economic, financial, and biological systems. Autoregression. Autoregression is a time series model that uses observations from previous time steps as input to a regression equal to predict the value at the next time gap. Autoregressive model. An autoregressive model can be used to represent a time series with the goal of forecasting future values. In such a model, a variable is assumed to depend on its previous values. The relation is also assumed to be linear, and we are required to fit the data in order to find the parameters of the data. Autoregressive process. An AR1 autoregressive process is one in which the current value is based on the immediately preceding value, while an AR2 process is one in which the current value is based on the previous two values. An AR0 process is used for white noise and has no dependence between the terms. Moving average. Now, a moving average is a widely used indicator in technical analysis that helps smooth out price action by filtering out the noise from random short-term price fluctuations. The most common application of moving averages are to identify the trend direction and to determine support and resistance levels. Now, a moving average is a technical indicator that combines price points of an instrument over a specified time frame and divides by the number of data points to give you a single trend line. It is popular amongst traders because it can help to determine the direction of the current trend while minimizing the impact of random price spikes. Examples of moving average. There are two main forms of moving average: simple moving average and the exponential moving average. A simple moving average is the most basic moving average, which is just a straight calculation of the mean price of a set of values over a given time period. If you were to calculate the SMA for a 10-day period, you would take the values of the last 10 days and divide the result by 10. Let's say that the last 10 days data of an asset were 80, 81, 82, 80, 82, 89, 82, 82, like that. So the moving average would add these figures together and divide by 10, resulting in an average of 82.2. The second type of MA or moving average is an exponential moving average, which gives more importance to recent prices to make the data more responsive to a new information. ARMA, autoregressive moving average. A ARMA models is simply the merger between the AR, that is P, denoted by P, and MA, that is moving average, denoted by Q models. AR model try to explain the momentum and mean reversion effects often observed in trading markets, market participant effects. MA or moving average, which is denoted by Q, models try to capture the shock effects observed in the white noise terms. These shock effects could be thought of as an unexpected event affecting the observation process. For example, surprise earnings, wars, attacks, etc. etc. Now, ARMA model attempts to capture both of these aspects. When modeling financial time series, ARMA model does not take into account volatility, clustering, a key empirical phenomena of many financial time series data. ARIMA is another model which is known as autoregressive integrated moving average. ARIMA, short of autoregressive integrated moving average, is actually a class of models that explains a given time series based on its past values, that is own lags and the lagged forecast errors, so that equation can be used to forecast future values. Now, any non-seasonal time series that exhibits patterns and is not a random white noise can be modeled with the ARIMA model. So an ARIMA model is characterized by three items, that is small p, d and q, where p is the order of the ART term, q is the order of the moving average term, and d is the number of differencing required to make the time series stationary. In a time series has a seasonal pattern, then you need to add seasonal terms and it becomes SARIMA. It becomes a seasonal autoregressive integrated moving average, short for seasonal ARIMA. More on that once we finish ARIMA. So what does the PDQ in ARIMA model mean? The first step to build an ARIMA model is to make the time series stationary, which has been cut, but it is to be understood. It is referenced to that. Why? Because term autoregressive in ARIMA means it is a linear regression model that uses its own lags as predictors. Linear regression models, as you know, work best when the predictors are not correlated and are independent of each other. So how to make a series stationary? The most common approach is to differentiate, that is subtract the previous value from the current value. Sometimes, depending on the complexity of the series, more than one differencing may be needed. The value of d, therefore, is the minimum number of differencing, is a method of transforming a non-stationary time series into a stationary one needed to make this series stationary. And if the time series is already stationary, then d is equal to 0. So next, what are the p and q terms? P is the order of the autoregressive, a time series model that uses observations from previous time steps as input to the regression equals to predict the value of the next time step. It refers to the number of lags of y to be used as predictors, and q is the order of the moving average term. It refers to the number of lagged forecast errors that should go into the ARIMA model. P is the parameter associated with the autoregressive aspect of the model, which incorporates past values. For example, for forecasting that if it is rained a lot over the past few days, you state it's likely that it will rain tomorrow as well. So D is the parameter associated with the integrated part of the model, which affects the amount of differencing to apply to a time series. You can imagine an example of this as forecasting that the amount of rain tomorrow will be similar to the amount of rain today, if the daily amounts of rain have been similar over the past few days. Q is the parameter associated with the moving average part of the model. If our model has a seasonal component, we use a seasonal ARIMA model, or known as SARIMA. In that case, we have another set of parameters, that is capital P, capital D and capital Q, which describes the same association as we have seen in case of ARIMA, that is P, D and Q, but correspond to with the seasonal components of the model. It becomes now SARIMA, and then PDQ small, non-seasonal, and capital PDQ for seasonal. Variation. One of the most important features of a time series is variation. Variations are patterns in the time series data. A time series that has patterns that repeat over known and fixed periods of time is said to have seasonality. Seasonality is a general term for variations that periodically repeat in data. In general, we think of variations as four categories: seasonal, cyclic, trend, and irregular fluctuations. Now, seasonal variation is usually defined as variation that is annual in period, such as swimsuit sales being lower in winter and higher in summer. Cyclic variations is a variation that occurs at other fixed periods, such as the daily variations in temperature. Both seasonal and cyclic variations would be examples of seasonality in a time series data set. Now, stationarity. Stationarity means that the statistical properties of a process generating a time series do not change over time. That means they remain stationary. This is a very important phenomena that we must understand. A stationary time series is one whose properties do not depend on time at which the series is observed. Thus, time series with trends or with seasonality are not stationary. The trend and seasonality will affect the value of the time series at different times. On the other hand, while noise series is stationary, it does not matter when you observe it. It should look much the same way at any point of time. In other words, a stationary time series is one whose statistical properties such as mean, variance, autocorrelation, etc. are all constant over time. Such statistics are useful as descriptors of future behavior only if the series is stationary. Some cases can be confusing. A time series with cyclic behavior but with no trend or seasonality is stationary. This is because the cycles are not of a fixed length. So before we observe the series, we cannot be sure whether the peaks and troughs of the cycles will be. In general, a stationary time series will have no predictable patterns in the long term. Time plots will show the series to be roughly horizontal, although some cyclic behavior is possible with constant variance. Now, types of stationarity. Models can show different types of stationarity. Strict stationarity means that the joint distribution of any moment of any degree, example expected values or variances, third order and higher moments within the process is never dependent on time. The definition is in practice too strict to be used for any real life model. The first order stationarity series have means that never changes with time. Any other statistics like variance can change. Second order stationarity, also called weak stationarity, time series have a constant mean, variance and autocovariance that doesn't change with time. Other statistics in the system are free to change over time. The constrained version of strict stationarity is very, very common. Trend stationarity models fluctuate around the deterministic trend, the series mean. These deterministic trends can be linear or quadratic, but the amplitude, height of one oscillation of the fluctuations neither increases nor decreases across the series. So difference stationarity models are the model that need one or more differencings to become stationary. Now, it may be difficult to tell if a model is stationary or not. Unlike the obvious example showing seasonality above, you usually can't tell by looking at a graph if you aren't sure that the stationarity of a model. A hypothesis test can help. You have several options for testing, including unit root test, augmented Dickey-Fuller test, or Zivot-Andrews test. A KPSS test, that is Kwiatkowski-Phillips-Schmidt test, run as a complement to the unit root test. A run sequence plot, the Priestley-Subbarao or PSR test, or wallet-based test, which are also a less common test based on spectrum analysis. Why is this stationary important? Because most forecasting methods assume that the distribution has stationarity. For example, autocovariance and autocorrelations rely on the assumption of stationarity. An observance of stationarity can cause unexpected or bizarre behavior, like t ratios not following a t distribution or higher r squared values assigned to variables that aren't correlated at all. Transforming models. Most real life data just aren't stationary. To quote Thomson in 1994, experience with real world data, however, soon convinces one that both stationarity and Gaussianity, a stochastic process, are fairly tales invented for the amusement. Differencing is where your data has one less data point than the original data set. For example, given a series ZT, you can create a new series yi is equal to zi minus 1, as well as its general use in transformations. Differencing is widely used in time series analysis. A series with no deterministic component, which has a stationary invertible arima representation after differencing of d times, is said to be integrated of order d. So this is how the time series can be explained, and this completes the time series and of course the supervised learning. Thank you.